So before I started recording here, I showed you the problem. We had that little styrofoam ball, and when we brought a charged rod nearby, you could see the styrofoam ball was first attracted, then repelled. Here's my point. It was feeling a force, but I wasn't touching the styrofoam ball. The problem that we have is that allows for what we call in physics action at a distance. Sarah, that allows for me to wave my fingers at you and have you somehow levitate off the ground. That's garbage. We cannot do that. So we have to have some kind of an explanation for how we're able to move something without touching it, or apply a force to something without touching it. The answer is no, we are touching it. We're just doing it invisibly. We're going to start out first looking at gravity. Gravitational field, you kind of take for granted because I introduced the concept to you last year of 9.8, negative if we wanted to make it down. If you have a mass sitting in outer space somewhere, that mass will send out a gravitational field in all directions. Nick, it'll kind of look like this, except I should draw the arrows differently. It'll kind of look like this. Sort of like the invisible tentacles of an octopus in all directions. Draw some arrows that look like that on big M. Now, that gravitational field is sitting there passively, but as soon as you put a second mass, a small mass like a satellite, in that gravitational field, that small mass will feel a force towards the Earth. So what we say, or towards the planet, what we say here, Emilio, is this planet was touching the satellite. It was touching it with the tentacles of an octopus invisibly that it was sending out in all directions that we call a gravitational field. It was sending out a gravitational field, and that's how it was able to grab that object. The reason the Earth can exert a force on the moon, Madison, is the Earth is sending out an invisible gravitational field, and that's how it's pulling on the moon. It's touching it with its gravitational field. We can't see it, but we know it must be there. Example 1 says, fill in the appropriate relationships. What was the force of universal gravity, the one with the big G in it? What was the equation? Anyone? Big M, Lim over. Okay. And then it says the definition of the gravity field. That's what I gave you for little g on your formula sheet. I said that it was defined as the number of newtons per coulomb. Okay. Then when we combined these two equations, we got it as an actual formula, big G, big M over R squared. Because the little m canceled. What were the units? Well, from this equation here, it would be, what are the units for force? What are the units for mass? So one way of measuring it, Keegan, was newtons per kilogram. We only really learned that this year. What units did you use for the 9.8 last year in Physics 11? There's kind of two ways to think about it. It meant that there were two ways to find gravitational field. If I knew the planet that was creating the field, I could use this one. If I didn't know the planet, but I knew how much of a tug a small mass was feeling, I could use this one. So example 2 says, find the gravitational field strength 8.38 times 10 to the 6 meters from Earth's center. Okay. Valerie, what does part A want me to find? We have two versions to find gravitational field. Which one am I going to use and why? They give you a hint. What did they give me? Am I going to use this one or this one? Second one. The gravitational field strength is going to be, let's write out the equation first. Big G, big M over R squared. Where big G was, we'll put it in our notes just this once, 6.67 times 10 to the negative 11. I'm doing that because you're going to start to notice today's topic looks really similar to this. Mass of the Earth I had one of you, by the way, on the test for one of the Earth questions unexpectedly use mass of the moon and radius of the moon, so preventable. I had one of you lose marks because they forgot to put units on their final answer. I had one of you lose marks because you forgot. What have I forgotten? Yes, squared. I know the gravitational field strength on the Earth's surface is 9.8. We're further up. I'm betting you're getting an answer less than 9.8, but I'm also betting you're not getting 0.000. It's probably going to be like 5, 6, or 7-ish. I don't know. It's a guess. What'd you get? So you're trying this on your calculator, yes? Keegan, what'd you get? 5.67. Anybody else? Is that rounded off properly? By the way, I had a few of you lose half marks because you rounded badly on the test. In fact, I think, what was it? 5.60. It was that a lot of several people rounded off that last digit wrong or forgot to. 5.68 units. I'm going to say newtons per kilogram, just because. Okay. Lena, what does B want me to find? Didn't we just find, don't write this down, didn't we just find gravitational field? Well, no. One way to find gravitational field strength is this one. We use that if they give me the radius. That's kind of the clue. Did they give me a radius? Oh, no, they gave me a test mass and a force. Which version of gravitational field has a mass and a force in it? We're going to use this one. It's going to be 750 divided by 10, which you might even be able to do in your head. I think the 0 will cancel on the top and the bottom, and we get 75 newtons per kilogram. Whatever object this is orbiting around, I would make a guess that it's a much bigger planet or star. Bigger planet than the Earth, maybe it's a small star, because 75 newtons per kilogram is roughly 7.5 Gs. Is that okay? Okay. That's not the theme of today's lesson. Today's lesson is about electric field. When I was making that ball move, I was touching it with the magic wand with an electric field in the same way that the Earth sends out, like the invisible tentacles of an octopus in all directions, a gravitational field. Charged objects send out electric fields. So could all of you please again draw some little lines, kind of like a sun, but this time put arrows on either ends, because like charges can repel, but unlike charges can attract, and so we have more than one option for direction. And that electric field is sitting there passive until another charge is placed in that electric field. But as soon as you put a small test charge in that electric field, that test charge is going to feel a force. By the way, so will the big charge, but in the same way as for Earth, we ignored the force that the satellite put on Earth. It does technically. We're often going to ignore the force that the test charge is putting on the big planetary charge. And in fact, you'll hear me kind of call this, I'll refer to this as the planetary charge. Here's my point, Claudie. There is a force, an electric force. Why did I put arrows on both ends? Because it's possible that like charges, which would mean little q would fall up, or unlike charges attract. But the mathematics is going to be almost identical to gravity field. It says, fill in the appropriate relationships. The force of electricity is K, big Q, little q, over r squared. Instead of doing Q1, Q2, I'll do big Q for the large planetary charge and little q for the little test satellite charge. What's the definition of electric field? It's going to be the same as for gravitational field. Our symbol for electric field is an E, capital E, with a vector sign. and it's going to be the electric force divided by the charge at that location, the force that a test charge feels divided by the magnitude of the test charge. So the electric field as a ratio, if you know the electric force, is that one. I'll come back to the screen, but Madison, I'm going to argue that looks an awful lot like this, except we're using E for electric field, and charge is behaving much like the mass did. What would the units for electric field be? What are the units for force? What are the units for charge? This was your new unit a couple of days ago. Yeah, so it's going to be newtons per coulomb. Oh, and just like gravitational field, there's another unit, not meters per second squared, but there is another unit that will work that we'll look at later. You could also plug this equation right there. You would find the little q cancels the same way the little m canceled. Another version of electric field is K big Q over R squared. Did I give you both of those on your formula sheet? But what do you notice about the Q's on your formula sheet? Are you going to put negatives or positives into this equation? If the charge is negative, do you put the negative into your calculator? So if you want to, you could add an absolute value sign there and an absolute value sign there. Units for electric field. Newtons per coulomb. And there is a second one. Volts per meter. But we'll put that in the notes a couple lessons from now. Volts per meter is also newtons per coulomb. Fine, you're nerds. Volts per meter. By the way, remember how I was figuring out the voltage when we were generating the sparks from the Van de Graaff generator? I was giving you a rough guess at that's about 200,000 volts. I know that air ionizes at about 3 million volts per meter. So as long as I took the 3 million and divided it by the meters, that would tell me roughly how many volts. As was the case with electric force, electric fields can't be positive or negative. A negative answer indicates attraction. You know what? We don't put negatives and positives in. This is why many textbooks will put absolute value signs around the Q's. Madison, what's A asking me to find? Find the... Keep reading. It's asking me to find the electric field strength. What's B asking me to find? Same thing. We have two equations. You've all turned the page. I'm going to suggest at the top of this page, let's write down E equals, one of them was FE over little q. And let's write down E equals K Q big Q over R squared. Now, I put vector signs over both of the E's. It's only asking for the magnitude, and the reason is I haven't yet told you how to figure out the direction. We have a weird situation. Gravity, the direction was always down. Is that always going to be the case with charged objects? No, because like charges repel. So we're going to have to come up with a rule for the direction. But first of all, at a certain point in space, a negative 0.5 microcoulomb test charge experiences a force of that toward the south. Find the magnitude of the electric field strength. Which version of electric field am I going to use here? Since we have two equations, which one am I going to use? Well, Quentin, what are the units on this number here, Quentin? So that must be A. Looking for where that starts letter F. Which one of those two equations has an F, a force in it? More specific, read it out so that everyone knows. Yep, electrostatic force if you want to be fussy. But you can just say electric force, I'll clue it. Or Fe over Q. Yeah, and little q, this is the tiny test charge. This is like the satellite that has just entered orbit around a planet. This is the test charge that has just entered the electric field from a big charge, a planetary charge. So it's going to be 5.2 times 10 to the negative 4 divided by 0.5. What do you got? What'd you get? Maddie? Did you get 0.0010 something? 0.00104. Or in scientific notation, 1.04 times 10 to the negative 3 newtons per coulomb. What does that mean? That means every coulomb of charge placed at this location will feel that many newtons of force. Great, and what does B want me to find? Which one am I going to use? Do you see how they gave me something in meters? That's a radius. So I'm going to use the one that has the radius in it. Which was which equation? Can you read it to me, kiddo? You wrote it at the top of the page, right? Yeah. K. Keep going. Big Q over R squared. So what was K? What was little k? On your formula sheet, it's 9 times 10 to the 9. Worth memorizing that one for this unit. It's fairly easy, 9 and 9, and you're going to get sick of looking it up. Spot where it is? Okay? Yeah, Sarah and Matt, you were away. What was big Q? Whoever's whistling can stop. Thank you. 2.3. And then what? Oh, micro. What was micro coulombs? 10 to the... What was micro? Negative 6, also you can look at that on your formula sheet, but that's worth memorizing. And again, clue in, if I say something is worth memorizing, it's really worth memorizing, right? Because, you with me, Sarah? Welcome back. All over 0.45, sorry for those of you on YouTube, squared. What do you get? You had 102,000, 102 and a bunch of twos? Okay. The first one that we did, part A, that is a very, 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 very small electric field. Usually, Zaina, you'll find our electric fields will be in the 10,000s or 100,000s. Okay? So, 1.02 times 10 to the 1, 2, 3, 4, 5. Units, Braden? Newtons per? Good. So that's how you can find the magnitude of electric field. How big at a specific location are the invisible tentacles of the octopus that are being sent out. Let's talk about the direction. This is the kind of so easy that it's tough, confusing point. So if you can, perk your brain up and look up. The direction of electric field with gravity was not an issue. Stuff always fell down. We had to define the direction, and here's what we decided. The direction of the electric field is the direction that a tiny imaginary positive test charge would want to go if placed at that point. It's which way would a positive at that location want to move if it could. But it's a tiny positive. How tiny? It doesn't have its own electric field because that would change the net electric field of that location and make it different. But it's which way a positive would want to move if it could. What's the direction of the electric field? It's the direction that a positive charge at that location would want to move if it could. And you'll kind of have to commit that to memory, but I'll be repeating that quite a bit for the next couple of lessons. So example 5, this is the same question that we just did, part A. It says, instead of finding the magnitude, though, find the direction of the electric field at a point where a negative 0.5 microcoulomb test charge experiences a force toward the south. I see a compass rose. Boy, did I botch that. Thank you. That would have been a weird universe. I was already answering the next question in my head. I don't multitask well, even in my brain. So you were smart enough not to copy me? Sarah wasn't. Okay. So, here's the test charge. What direction is it feeling a force? What's the polarity of the test charge? That's a fancy word for, is it negative or positive? So which way is a negative charge feeling a force? Which way would a positive charge sitting right there feel a force? We had to define electric field in terms of something, Madison, and we decided we'll define it in terms of a positive charge. Because unlike gravity, where stuff always fell down, we have the issue where stuff can fall up. So one possibility is you'll know the direction of the force at a location. If what you're looking at is positive, the force will be in the same direction. If the charge at that location is negative, the force will be in the electric field, sorry, I said force. The electric field will be in the opposite direction. The electric field 0.45 meters to the right. So I think we're talking right there. Put a little X right there. Better yet. Put a little plus right there. There's our positive test charge. How tiny? So tiny it doesn't bring its own electric field with it because that would change the question. So it's imaginary. But it is positive. Which way would a positive want to move if it could? Well, our planetary charge, what's the magnitude and polarity of our planetary charge? Big Q, positive or negative? How do you know? Right there. They didn't put a minus sign. So if you want to, I'll put a little plus sign there as well. Which way will this test charge want to move if it could? Will it be attracted towards or repelled away? How do you know? Because like charges. What direction is that? Right? So again, we had to define the direction somehow, and the convention that scientists decided upon, Chloe, is we're going to use which way would a positive at that location want to move if it could. Example C says draw the electric field around a positive charge. Let's make it a proton. So do me a favor, draw a line there, a line there, a line there, and a line there. 4 lines. Imagine a little positive charge right here on the top line. Which way would it want to move if it could? Well, is it like or unlike to this proton? Like charges. So which way will the electric field point above the proton? Which way will the electric field point right here? Which way will the electric field point at the bottom? Which way will the electric field point at the bottom? Which way will it point? Jan, which way will it point right here? Okay. What would the electric field look like around a negative charge? It's a good question. Well, again, let's put 4 compass lines. Which way would a positive along this line want to move if it could? So here's my question. Look up. Don't write this next bit down. If I didn't tell you the polarity, could you figure out from the electric field diagram whether it was positive or negative? I will do that sometimes. Probably multiple choice or in your homework. I won't tell you the polarity, but I'll give the electric field diagram. Okay? Let me pause for a second here. Look up, please. Say, going to get off your phone before I lovingly snap. Let's put a charge there. Is this charge positive or negative, and how do I know? How do you know? Because the direction of the electric field, which is the direction that a positive charge would want to move if it could, is telling me that. What if I put a second negative charge there? Like charges repel. They're going to interact with each other. In fact, if I just muck around with this, now they're going to start to interact with each other. And this is going on all the time at the atomic and subatomic level. I'm going to add another charge, but I'm going to add the next charge, and I'm going to make it positive. At the back, you can't see, but I just deleted a negative sign. So I'm going to add a positive charge, and now things are really going to get a little bit chaotic. Stuff is moving all over the place. This charge right here, positive or negative, and how do I know? What about this charge right here? What about this charge? Is that another one? This is the atomic dance that's going on all the time. Okay? This charge right here, positive or negative, and how do I know? Why? Because a positive nearby would be repelled. Okay? So we had to pick a direction for electric field. We went with which way would a positive want to move if it could. What's the direction of the electric field? We ask which way would a positive at that location want to move if it could. There's a shorter version of this from positive to negative, and some textbooks teach that. The problem is if you only have a positive or if you only have a negative in your picture, it's tough to see from positive to negative. So I use the slightly longer definition. I think it's a little bit clearer. And all of that is to build up to this next question. I like example 6. I like example 6. Example 6 is a nice question. How do we find the net electric field? Right, it's still there. We're good? How do I find the net electric field of 2 or more overlapping charges? We're going to use something similar to what we did last lesson, what we called the principle of superposition, which is a fancy phrase for we do them one at a time. So it says, find the electric field, magnitude, and direction at the indicated point right there. How many charges are there in this picture, Lena? I'm going to label them with numbers. I'm going to call this Q1, Q2. And what I'm going to do is I'm going to find the electric field from Q1, magnitude and direction. Then I'm going to find the electric field from Q2, magnitude and direction, and then I'll add them vectorially. If they're in the same direction, I'll just add them. If they're in opposite directions, I'll go winner minus loser. Let me pause. Which version of electric field am I going to, which equation for electric field am I going to use? Did they give me distances? The one with the R in it. Which, Nick, was what? Big Q. Okay. What was K? 9 times 10 to the 9th? Big Q, 1 times 10 to the, what was microcoulombs? 10 to the, worth memorizing that. It's on your sheet, but trust me, I've done you a fave. What's R? What's R1? Nick, what's the distance between charge 1 and the field point? Okay. Maddie, put your calculator down. Maddie, what's 9 times 1 divided by 1 squared? There's going to be a 9 in my answer. Now we just got to deal with the powers of 10. 10 to the 9th times 10 to the negative 6. We add the exponents. Units, Nick. Per Coulomb. Ready, Nick? Here's the hard part. Direction. So pretend this charge doesn't exist. Which way would a little positive right there want to move because of that guy? Would it be attracted left toward or repelled right away? First of all, is this charge here positive or negative? Is this charge here positive or negative? Are they like or unlike? Like charges. So the direction from this guy to the left or to the right? Yep. Right. Repeat for electric field number 2. I'm not going to rewrite the formula equation. I'm going to go to numbers. It's going to be 9 times 10 to the 9th. Maddie, what's R this time? Don't say 4. Thank you. Common mistake that kids make. So it's going to be over 3 squared. Oh, what's Q? Also 1 microcoulomb. Now, if you did type that first one into your calculator, it's really all you're changing is the 1 on the bottom to a 3. However, you could, if you were clever, Maddie, realize that this is 9 divided by 9, which is, I think it's going to be, is that okay? Oh, direction, Maddie, your turn. Which way would that positive feel a force because of charge 2? Would it be repelled left or attracted right? Everybody, how will I add 9,000 right to 1,000 left? Winner minus loser. Yeah. So what's the net electric field? We'll write it out. I realize most of you could do it in your head, but in our notes, let's write down what we did. We went 9,000, take away 1,000, 8,000 newtons per coulomb. Direction? Okay. There's going to be a find the net electric field. The 2 points will be in a straight line with each other and the field point. But look up, I could put the field point between them. I could put it there as long as I give you the right distances. Or I can put it there as long as I give you the right distances. And you'll have to figure out what the direction of each electric field is at that location and then add them vectorially. Example 7 says, draw approximately the resultant electric field at the indicated field points. Assume they're both identical positive charges, 1 microcoulomb. I'm going to start in the middle here. Don't write this down, look up. What direction would this charge have as an electric field right there? Which way would a positive right there want to move because of, you know what, I am going to call it Q1 and Q2 so you know what the heck I'm talking about. So the electric field from Q1 in the center, which way would it be applying a force, Sarah? Put the phone away. Oh, I'm sorry. I thought you were on a phone. My bad. Okay, so positive will be pushing that way. Don't write this down. Which way will the electric field from this charge be right here? Okay. How will they compare with each other in magnitude? Why? Same charge, same R. So if you have, for example, 5 left and 5 right, what's your net electric field? The electric field right there in the middle would be 0. There would be a spot right there where a charge would not feel a force at all. Okay. What about right here? Well, don't write this down, just watch. This would be exerting an electric field to the right. What direction would the electric field from Q2 be right here? To the left? Bigger, smaller, or the same size as the electric field from Q1? So what's bigger to the right plus smaller to the left going to be? So if all of you could draw an electric field that looks like that. What about over here? Good. What about above the middle right here? Well, don't write this down, just watch. I think the electric field from Q1 would be in that direction, maybe not that long, but in that direction. The electric field from Q2 would be in that direction. How would I add those two together? Draw them tip to tail? You know what? Let's try that. What direction is the resultant going to be? Yeah, you know what? The electric field right here would be straight up. I don't know how big it would be, Madison, but it would be straight up. The trickiest one is right here, but I can figure it out because the electric field from Q1 would be in that direction, and the electric field from Q2 would be kind of weak, but in that direction. I think the resultant would be mostly straight up, but still getting pushed sideways a little bit. I should warn you, there is a bonus video game challenge that will require you to become intimately familiar with how overlapping fields behave. I should also warn you, it is by far the most addictive and irritating bonus challenge that I will be giving you. I will be showing you some photos, screenshots, and videos to demonstrate my point. It may end up consuming your Christmas holidays if you end up down that abyss of frustration. But I'll smile over that. Sorry? Patience. Example 8 says, draw the electric field pattern for equal like charges. So these are both positive. So the fact that they're both positive, are the arrows going to point towards the charges or away from the charges? Okay, just watch and look up. Draw afterwards. Here is my argument. I think an electric field line would head out from this one, but it would get repelled and get kind of veer up and away. Okay, you guys watching? I think an electric field would head out here, it would get repelled and veer up and away. I think an electric field from here would kind of go like that, and like that, like that, like that, and then the bottom would be symmetrical but the same. So like that, like that, like that, like that, like that, like that. Try kind of sketching something like that, please. I'll come back to that in a second, but here is a lovely sim. Here is one positive charge. Here is another positive charge. And if I just show you kind of the direction, that's sort of what it should be looking like. You can see right between them, there's no electric field. They'd cancel out. You can see above them, the electric in the middle, the electric field is nearly vertical as they kind of repel each other that way. Beneath them, very, very similar. If I bring out an electric field sensor, This will show you the direction of the electric fields in all these locations. So, kind of like that. What about for equal but opposite charges? Well, one of the big differences, and I'll do this one in red so you can see the different lines, would be, boom, straight across. Because the positive would head away from the positive and also be attracted towards the negative. And in fact, this line right here would arc and end up getting pulled towards the negative. This electric field line would end up down there. There would be an electric field line that would start going away and get pulled in there. It's kind of going to look like a big bug or something like that. Kind of looks like a bug's head or an ant's head or something. But it would be kind of like that, except there would be trillions of those lines. I'm just doing a very general kind of, this is the idea, what it might look like. Let me show you on the sim again what it would look like. So let's get rid, I'll bring up my drawing in a second. Okay. Get rid of the sensor. So straight across, and then otherwise you can see everything kind of arcs. Whoop, don't move it, Mr. Dewick. Everything kind of arcs towards it and arcs towards it. Kind of like that. Okay. I've got some better pictures that I stole from a textbook on the next page. The concept of the electric field originated with Michael Faraday. Michael Faraday, one of my nerd heroes. I'll go on a Michael Faraday rant another time. But Michael Faraday, I got to go on my Michael Faraday rant. Let me just see, how much more of this lesson do I have to finish? Okay. Put your pencils down, look up. Okay. Michael Faraday was born at the end of the 1700s, 1791. He was born into, a very poor family. He got a job as a teenager, because this was before people could get educated if you were poor. He got a job as a bookbinder. This is back when books were sewn or glued by hand. So he knew how to read and write. At that time, the aristocracy scientists would do public lecture shows. In fact, the lecture shows are still ongoing. It's called the Christmas lectures, where they would invite the public to come and they would show the latest scientific wonders to the lay public, and ooh and ah. And one of the scientists at the time was Sir Humphrey Davy. He did a bunch of demonstrations of electricity and things like that. And Faraday was given a ticket, and in the audience he took copious notes, very, very good notes, bound them into a book, and he sent them to Mr. Davy. And Mr. Davy saw this book, saw how neat it was, saw how well done it was, and said, I'm going to hire this guy as my assistant. Probably the best hire in history, because for the next 30 years, Humphrey Davy stole every one of Faraday's discoveries, and Michael Faraday was too humble and grateful to say anything about it. We now know most of the things that Humphrey Davy took credit for, Faraday discovered. Faraday was maybe the greatest experimentalist in history. If you needed someone to come up with an experiment that would eliminate every other variable but the one you were interested in, he was your guy. And he would obsess over it. He had very, very lousy math skills. In fact, most of his discoveries he wrote out in English because he could not come up with the equation or the formula. And so we also have these electric field lines as his visualization of some complicated math. He is basically the father of modern electricity. Among other things, he invented the electric generator and the electric motor, which we use those all the time. There's a famous story. He was demonstrating some of his discoveries about electricity to the British Parliament, and one of the lords in Parliament said, what use will this be? And Faraday wisely said, I think you'll be able to tax it someday. That's a great answer to a politician. He got his funding pretty quickly. Oh, okay. When he died, he was famous. I mean, he was the father of electricity. Queen Victoria offered him burial in Westminster Abbey near Isaac Newton, he turned it down. He was a very, very humble religious person, which is one of the reasons why he lived with Humphrey Davy, ripping off all of his discoveries for all those years. Nah, I'll just regular plot for me. He's one of the few people, maybe the only one, I'd have to look it up, to turn down burial in Westminster Abbey, which doesn't happen very often. So there's my nerd hero. I'm going to pause for a second. I promised you an addictive video game. So at the very, very end, you can add this. If you Google PHET, electric field hockey. I know this will work on a PC, on a Windows machine. I don't know if this will work on a Mac. Sorry, because it was originally written in Java. Let me pause. So this is the link. When you click on it, it'll ask you if you want to run in the browser-compatible version. Jan, you want to? I haven't tried this on a Mac. This is what I don't know will work or not. And it's sort of what it sounds like. You'll have a screen that looks like this. Here is your hockey puck. There is the goal. And one way to get it to score a goal is to use like charges repel. You get no points for that. Reset, clear. Level 1, I guess I could do that, and then once it got over here, maybe I could bank it back. Oh, let's put a negative in the goal to attract it to the goal. Let's see what that does. That was a fluke. That's the first time I've ever got it the first time. You get no points for level 1. Nothing for that. Level 2, I'll give you 1 point if you send me a video of you beating level 2. Level 3, I will give you 2 bonus marks if you send me a video. You cannot get 3 bonus marks in total, though. So if you do this one, that voids level 2. Except I won't for level 3. You're not allowed to bank it off the screen, around the screen, and come back. That's a glitch that my kids found out a couple of years ago. So now I'm not letting you do that. Okay? I told you that this was frustrating. No, that voids the game. So if you touch the... Oh. Dunk. Okay? So you can't touch the blue. Good question. Pause.